Picking up where we left off in the last video, sometimes we evaluate the limit and we find that our two functions grow relatively at the same rate. And this is what the result is going to be when that's telling us that f of x is kind of sort of exhibiting, for large input values, the same behavior as g of x is. So if we evaluate the limit and we don't get 0 and we don't get positive or negative infinity, we get some real number or value that tells us that whatever g of x is doing, whether it's converging or diverging, f of x is doing the same. So getting a real number value result out of that limit is extremely helpful. So this tells us that both functions either diverge together or converge together. But it's super important that we know what the function on the bottom is doing. So that's helpful as well. So let's practice this. Does the integral converge? This is the integral from 4 to positive infinity of 1 over the quantity x cubed plus 2 dx. Well, if it was a u substitution, and I'm sure many of you see right now that it's clearly not, because I need an x squared up in the numerator to go with my dx, and it's not there. So this is not a u substitution. I have a problem here. Thank heavens they're just asking me about convergence or divergence. So if I could determine what another function is doing over the same interval, let's try this one. This is one that I actually can evaluate. We might write it like so. This is a power rule, right, for integrals. So the antiderivative to this would be 1 over n plus 1, so negative 1/2 x to the n plus 1 plus c. That's what I would get for the indefinite, but this is a definite. So let's plop that inside our limit. We would show the AP reader that we are evaluating this integral, and our result would be the limit as b approaches infinity of negative 1/2 x to the negative 2 from 4 up to b. And so we would write this as the limit as b approaches infinity of, I'm going to put negative 1 over, instead of 2x squared, though I'm plugging in b for x. So there's my upper limit, minus my lower limit, which is going to be negative, so I'm going to make that positive, 1 over 2 times 4 squared. And all of that is inside my limit. So as b heads toward infinity, that's negative 1 over huge. This term is headed toward 0. So this converges to a value of 1 over 32. So it converges. So I have determined that 1 over x cubed converges. And if I could plop that in a limit as x approaches infinity and put that function on bottom and my unknown function, 1 over x cubed plus 2, in the top, let's see what the relationship is. Now, we haven't evaluated it, but we just determined that our function on bottom, what we called g of x a while ago, converges. So what do I want as a result out of this limit? Which of those results would be helpful? This tells me they behave the same. So that would be helpful. This tells me that my numerator is smaller than my denominator function. So that would be helpful. This tells me that my numerator is bigger than my denominator. And since the denominator converges, these are the two results I'm looking for. If I evaluate this limit and I get infinity as a result, then my choice to compare the given function, the given integral, to the function 1 over x cubed was a bad choice, and I would need to make another choice. Hopefully we've made a good choice here. So let's clean this up, the limit. As x approaches infinity, I'm going to flip the bottom function, x cubed plus 2, and we have infinity over infinity. So we'll do a step of L'Hopital's. Numerator is 3x squared, and denominator is 3x squared plus 0. Well, 3x squared over 3x squared is 1. That is a good result. That's a real number. That's not 0. So this tells us, this result says, since 1 over x cubed plus 2 is smaller than 1 over x cubed, and the integral from 4 up to infinity of 1 over x cubed dx converges, then the integral from 4 up to infinity of 1 over x cubed plus 2 dx must also converge. So there's an example of how we use that limit and the comparison of two functions to talk about convergence and divergence for an integral that we don't know how to solve. Now, this whole limit comparison idea is not the only tool we have in our toolbox. Here's another one where we're not going to use the limit. We're going to see what else we can do to try to determine whether this area converges or diverges. So does the area trapped in the plane between e to the negative x squared and the horizontal axis from 1 to positive infinity, an unbounded area, does that area converge? Well, we're going to compare with one integral that we have proven already in our first video. You can go back and look at your notes. We proved that that does indeed converge. So how would I compare, not using the limit, how would I compare those two functions? What do I need to show the AP reader to use this as a result? What I need to show is that 1 over e to the x squared is less than 1 over e to the x, because I am comparing to a convergent function. Then I need to prove the one that I don't know, the one they've given me to explore, is smaller. And when you have fractions like this, when you have ratios, all you have to show the AP reader is, look, I understand that this is the relationship between their denominators. I understand that for any positive values of x, e to the x squared is greater than e to the x. That's true for any positive value of x you want to put in there. And if that's the case, when I put those in the denominator of a fraction, here I am dividing by a bigger value. This has a bigger denominator than this function does. And if I'm dividing by a bigger number, then the fraction's going to yield me a smaller output. And that's all we have to show the AP reader. That's a direct comparison. We did a direct comparison, not using the limit, on what's going on the outputs of these functions for the x values that we're interested in, positive x values. And so we would answer this and say, since the integral from 1 up to infinity of e to the negative x dx converges, and 1 over e to the x squared is less than 1 over e to the x. Now understand something, this already has to be on your paper. You can't just go directly here. Look how much happened in your head. Anything that happens in your head has to be on paper. This has to be there as well. So since we've established for the AP Reader that we know this is true, that this integral converges, and that the relationship between those two functions is this, then the integral in question, the one that they're asking us about, must also converge. So not a lot of calculus going on there, just a lot of thinking. Just a lot of reasoning your way through these things and showing the AP Reader what's going on in your head. One thing I want to say for sure before we move on. Here we were integrating these two functions. The blue function is 1 over e to the x. The red function is 1 over e to the x squared. And we were integrating from 1 to positive infinity. And so everywhere over that interval, it is true that the function we were talking about was less than the function we knew. And what if this integral had been from 0 to positive infinity? Would that make a difference? Because clearly from 0 to 1, 1 over e to the x squared is bigger than 1 over e to the x. Well, it turns out that when we're talking about convergence and divergence, we don't care what's happening near the origin, or we don't care about small input values, and small is relative to infinity. So frankly, I don't care what's happened for the first million, billion, gazillion inputs. They can have a different relationship. What I care about is what's happening near infinity. That's where convergence or divergence occurs. Near infinity is what I am concerned about, near large input values. All right? And a final example here. Here is an integral that we could actually evaluate. We can just get right down to the business of evaluating this integral. It is a u substitution. It's one that we can evaluate very easily. So we would say the limit as b approaches infinity, this is a u substitution where u is negative x cubed, du negative 3x squared dx. So this is e to the u du. We're off by negative 1/3. So the antiderivative that we're going to be using looks like so. So our antiderivative is negative 1/3 e to the negative x cubed, and we're evaluating from 0 up to b. So fundamental theorem, every step of the way, ladies and gentlemen, you better be putting your limit notation. Now again, because we're headed toward infinity, I put that negative exponent, made it a positive exponent, put it down in the denominator. So there's my upper limit evaluated at b. And a minus negative 1/3 e to the negative 0 cubed is just 0. So for large input values, this denominator is huge. Negative 1 over huge, that term's going to 0. E to the 0, please remember, is 1. It's not e. So this is converging, and it's converging to a value of 1/3. So there we are, and c is 1/3. So there's the correct answer. All right, so now we've worked a little bit more with convergence and divergence. We know we can compare functions inside a limit. We know we can directly compare functions. There are going to be many improper integrals that we can just out and out evaluate, just like this one. So you need to look at the integral that you're given and decide what technique you're going to use to actually determine convergence or divergence. So come to class next time. We'll work some homework problems.